Welcome to Lecture 8 in Mathematical Foundation of Robotics. This lecture is entirely devoted to trigonometric functions, which play a pivotal role in robotics. We will now introduce this function, and these functions are usually referred to the unit circle, which is a circle centered at the origin with radius equal to 1. So these are the xy axis, and the Cartesian equation of the circle is x squared plus y squared equal to 1. So radius is equal to 1, and the circumference is given by 2 pi r, which in this case is just 2 pi, and instead the area is equal to pi r squared, which means just pi. Okay, so we will refer to this circle, and we'll start by introducing the concept of arc. Now, if we again consider this unit circle of radius 1 centered in the origin, and we pick a point P, and we call this point A, which is the intersection with the x-axis, and we imagine that we want to reach P moving along the circle counterclockwise. If we travel for a length alpha, we say basically that the point P corresponds to an arc alpha if the arc AP, this is the symbol of arc AP, has length alpha. Now, by convention, if alpha is less than 0, the circle is traveled clockwise, and if alpha is larger than 2 pi, the circle is traveled more than once. Okay, so we have now a correspondence between the point P on the unit circle and the arc, and we can establish a similar correspondence with the circular sector. So this is the unit circle. We consider the usual point A, a point P, and we want now to establish a relationship between the position of the point P and the area of this circular sector. Okay, and this correspondence is unique once again, so we say that P corresponds to a sector alpha if the area of the circular sector OPA is alpha divided by 2. In fact, it is easy to find the area of this circular sector by considering the direct proportionality between the area of the sector and the length of the corresponding arc. In fact, we can say that the area divided by the length of the arc is just equal, well, this ratio is just the same if we consider the entire area of the circle, which is pi, and the entire circumference, which is 2 pi. And from this, clearly it follows that the area is just equal to 1/2 of the length. Of course, that means just 1/2 alpha. Good. So now that we have established a correspondence between the position of a point P on the circle and the arc, we can say that we can define the point P. So let's once again represent the unit circle, and let's just consider the first quadrant. We can say that the point P, the generic point P, that is on the unit circle can be defined in terms of its x and y coordinate. And we say that the x coordinate of P, we call this cosine of alpha, which is basically a function of the arc alpha, and instead we say that the y coordinate is the sine of alpha, so it's a function of the length alpha. So we can rewrite this by saying that P, the point P, is defined in terms of its Cartesian coordinates, which now are cosine of alpha and sine of alpha. In fact, we know that P corresponds to a specific length of the arc, and for this length we are defining its Cartesian coordinates as a function of this length. We can do more than that, because in fact we can draw the tangent to the unit circle at the point A and find the intersection with the radius passing by P, and we see that this length is what we call tangent of alpha, which is basically the length of this segment, which is intersected by the tangent, the vertical tangent to the unit circle at the point A, and the extension of the radius passing by P. And it is easy to see that clearly this comes from the similarity of these two triangles. If we call this OAB and we call this OCP, you see that the triangles, by the similarity of the triangles OAB and OCB, what we have is that AB, the ratio of AB and CP is equal to the ratio of OA and OC. But AB by definition is just the tangent of alpha. CP is the sine of alpha. OA is equal to 1 because it's just the radius of the unit circle, and OC is the cosine of alpha, and therefore we have that the tangent of alpha is nothing more than sine of alpha divided by the cosine of alpha. So we have defined for the point P three functions: cosine of alpha, sine of alpha, and tangent of alpha. We can now extend the definition as a proper function with the real variable. We'll do this and we'll start with the sine of x. In fact, we can consider this function of f of x to be just the sine of a generic angle x. Now, of course, there are two possible ways of defining a function. If we consider f from R to R, so this is to say, if we consider any possible real angle x, what we get is that f of x equal sine of x is an odd function with minimal period equal to 2 pi. And in fact, the graph of this function is the following. And it is always between -1 and 1, and we clearly see that this function is an odd function because if we refer back to the unit circle, clearly we see that if we consider this x and this minus x, clearly this is the sine of x and this is the sine of minus x. We clearly see that the sine of minus x is equal to minus sine of x. So yes, this is indeed an odd function that repeats itself every 2 pi, because clearly if this is 2 pi, this is the minimal period. Okay, good. Clearly we see that this function is not injective nor surjective. So if we want to invert this function, we need to change the domain and codomain. And we say that if we consider f from minus pi over 2 to minus 1, which is just like saying that we are basically consider only this interval, this part of the function. So I will repeat drawing here. We are now taking only what happens between minus pi over 2 and pi over 2, and we know that this will be the function. Clearly this function is surjective and injective, therefore it is invertible. And why it is invertible? Well, it is invertible because the function f of x is strictly increasing and is invertible, and the inverse function, is the following. Let me call this g, that goes from minus 1 to minus pi over 2. So this will be the inverse function. Now we go from minus 1 to minus pi over 2. to plus pi over 2, and the graph of the inverse function will be just this. We can think of obtaining this graph by just reverting the x and y axis from the previous graph. Okay, and this function is called g of x is called arc sine of x, and it is another odd function. In fact, we see once again that if this is the arc sine of minus x, this is just equal to minus the arc sine of x. So it is another odd function. Good. Let's now move to the other function that we have defined when identifying the position of P on the unit circle, namely cosine of x. Similarly, we can say that f of x is equal to the cosine of x, and if f of x, if we consider f, this function, from R to R, we have now an even function, because this will be the graph of the cosine. Let me extend this. The graph of the cosine, something like this, and we immediately realize that this is an even function, because the cosine of minus x is just equal to the cosine of x, and it is not injective nor surjective, but has a minimum period, once again, of 2 pi. Well, the fact that the minimal period is 2 pi is just a consequence of the fact that we are moving more than once on the circle, and we encounter once again each of the value from the first round. Again, we can restrict this function f from the interval 0, pi to minus 1, 1, which is just like saying that we are now considering only this part of the function. And if we do this, of course, the function will now become, f is now strictly decreasing and invertible. And what will be the inverse of this function? Well, the inverse of this function now, of course, let me call in general this function g, so the inverse is g of x equal to the arc cosine of x, and again we can obtain this easily by just swapping once again the graph. Now, of course, this function g goes from minus 1 to 0 pi. So this will be pi. This of course is 0, this is 1, and this is minus 1. Okay, and yeah, so this is the inverse function. Let me write g of x equal to the arc cosine of x. We have now for both sine of x and cosine of x the inverse functions. It's time now to consider the last trigonometric function, which is the tangent of x. So we will consider now f of x as the tangent of x. But the tangent of x, remember the tangent of x is defined as sine of x divided by cosine of x. So now we should consider basically this in general is defined on a subset of the real number a given by all the real numbers except the angles pi over 2 plus k pi for any k belongs to the signed integers. In fact, in these angles here, this is where cosine of x is equal to 0, so clearly tangent cannot be defined on those angles. So in the first option is just to consider f from a to r, and in that case what we get for tangent of x diagram like this, where this is minus pi over 2 and this is pi over 2, and this will repeat again periodically. Okay, so of course this is minus pi, this will be minus 3 pi over 2, in this case this is pi and this is 3 pi over 2, and so on and so forth. So we have an odd function because we see from this diagram that tangent of minus x is equal to minus tangent of x. So this is clearly an odd function, and of course is not injective, even if it is surjective, but it is not injective, as we can realize when we draw an horizontal line. We see that this horizontal line crosses the graph of the function many times. So we need to restrict the function, for example, to the subset minus pi over 2 plus pi over 2. And of course with excluding minus pi over 2 and pi over 2, and as a codomain we just pick the entire R. Then the function is now strictly increasing, and it is invertible. What will be the inverse function? So we are saying that we are now taking only this part basically. So this is the part of the function where we do the inversion. The inverse function now, so the inverse function is g that goes from r to minus pi over 2 plus pi over 2, and it is called g of x arc tangent of x, and it turns out that it is another odd function. Can be easily obtained as always by reverting the graph, and what we get is this, that of course will go from minus pi over 2 to pi over 2. So this is the arc tangent of x. Now this seems quite clear. However, when actually doing calculation, it is very easy to make mistakes. So for example, let's consider this expression: arc sine of 1 and arc sine of 2. Okay, so one might be tempted to answer 1 to the first and 2 to the second because we are just applying the inverse function to the function itself. So we are saying in the first case arc sine of sine, arc sine is the inverse of the sine, so this will give me back 1, and the second, for the same reason, will give me back 2. However, the first one is correct, the second one is not. Okay, so this is a big mistake. This cannot be 2. The reason is that the codomain of the arc sine function is minus pi over 2 pi over 2. So the thing is that it must be in the interval minus pi over 2 and pi over 2. In fact, if we go back to the definition of the arc sine, this was the definition of the arc sine, and when evaluating the arc sine of a function, we saw that the codomain is basically minus pi over 2 pi over 2. So because 2 goes beyond this interval, it is impossible just to give 2 as a result of this. Okay, so we can generalize this result saying that in general, if we evaluate arc sine of x, we can say that this is equal to x for only x that belong to the interval minus pi over 2 and pi over 2. Similarly, if we apply the arc cosine to the cosine of x, we can say that this is equal to x only if x belongs to the interval 0 pi, and if we apply arc tangent to the tangent of x, this is equal to x only if x belongs to the interval minus pi over 2 and pi over 2, because this is basically where the tangent function is invertible. Okay, so this is the codomain of the arctangent. Okay, so somehow these three hold because of we need to take in consideration the domain of the functions. And similarly, we can say that the sine of the arc sine of x is equal to x, of course only if x belongs to minus 1, 1, because this is the codomain of the function. Cosine of arc cosine of x is equal to x, again for every x that belongs to minus 1, 1, and tangent of the arc tangent of x is equal to x, well, this time for every real number x. So, and this is because of the codomain of the functions. Well, we can say that when trying to solve equations that involve the inverse function, it's always good to resort to some pictorial representation. Let's suppose, for example, we were trying to solve the first equation, which is arc sine of 2, okay, and we saw that this cannot be 2, okay, so we're trying basically to solve this problem. So we have the unit circle, and we are saying, okay, what is the sine of 2? What would be 2 radians? 2 radians will be somewhere here, because we know that, just as a note, 1 radiant is almost 60 degrees. So we can say that basically 2 radians is almost 120 degrees, right? So yeah, it makes sense that the this point represents 2 radians, okay? So this would be 2 radians, the arc of 2 radians. So that implies that this would be the sine of 2, okay? So we need to find what is the arc sine of 2. But if we remember that the codomain of the arcsine function, which is nothing else than the domain where the sine is invertible, is this interval, which is between minus pi over 2 and pi over 2, we have that the solution is exactly this one. So this will be the arc sine of 2, right? So it is just the intersection between this line that represents sine of 2 with the codomain of the arcsine function. Similarly, if we have to solve an equation for the arc cosine, and let's say, for example, that we have an equation like arc cosine of some value lambda, so because the domain of the arc cosine is this one, and let's suppose that this would be the cosine of lambda, well, in this case the solution to the equation is clearly given by this. This will be the solution of the equation, because it will be identified by the intersection between the codomain of the arc cosine function and the line representing the cosine of lambda. Final example. Once again, let's consider the unit circle. And let's say now that we are trying to solve arc cosine of lambda, but now for example, let's say that we are trying to solve for the cosine of 4 radians, okay? And we know that 2 radians is here. 4 radians will be somewhere here. So we have this line. This represents the cosine of 4 radians. And the solution of this equation, again, we need to find the point that belongs to the codomain of the function. So we have that this will be the solution of this trigonometric equation. Let's conclude this lecture on trigonometric function with an important formula that will be relevant in the future. And the formula is the following. Arc tangent of x plus arc tangent of 1 over x is equal to pi over 2 for every x larger than 0. So this formula relates the arc tangent of an arc x with the arc tangent of the inverse of the arc, and this is valid for all x, all positive x's. Okay, in fact, we know that the arc tangent, let me remind you just here what is the arc tangent of x. If this is the arc tangent of x, we know that the arc tangent of x is defined over the entire r, but we are now just considering this part of the graph, okay? We are just considering this part of the graph only for x larger than 0. So actually, arc tangent of x is defined on the positive x-axis, and the same is true also for the arc tangent of 1 over x. Okay, let me prove this formula. Let's say that alpha is equal to arc tangent of x, and at this point we know that this is defined, okay? But what we see from the graph is that this alpha belongs to the interval 0 pi over 2, right? So this is the definition of alpha, right? Just because of the restriction of arctangent of x only to positive values. And let me now evaluate pi over 2 minus alpha. Well, because alpha is defined in the interval 0 pi over 2, of course also pi over 2 minus alpha belongs, this must belong to the same interval, 0 pi over 2, extreme excluded. So that implies that the tangent of pi over 2 minus alpha, which remember is just the sine of pi over 2 minus alpha divided by the cosine of pi over 2 minus alpha. Well, we know from elementary trigonometry that this is just equal to 1 divided by the tangent of alpha. And right, so this is equal to 1 over x, y? Well, because clearly we know that since tangent of alpha would be equal to the tangent of, let's review the definition of alpha, of the arc tangent of x. And because we are in the interval 0 pi over 2, we know that this is well defined, so this is equal to x. Okay, so this proves basically that the 1 over tangent of alpha is just equal to 1 over x. Okay, so we're almost now at the end of the proof, because at this point we know that pi over 2 minus alpha is equal to arc tangent of 1 over x. And this will conclude the proof.